The paper proposes a mini-batch method for solving nonlinear partial differential equations, PDEs, using Gaussian processes, GPs. The main challenge in GP-based methods lies in the inversion of a covariance matrix, whose cost grows cubically with the size of samples. Inspired by neural networks, the authors develop a mini-batch algorithm to update the GP model, reducing the computational cost to each iteration. The authors employ a stochastic proximal algorithm to solve the requisite minimization problem over function spaces. The objective function in the minimization problem cannot be depicted as the expectation of a finite-dimensional random function, making a naive deployment of stochastic gradient descent challenging. The proposed mini-batch method takes a mini-batch of samples at each step to update the GP model. Using stability analysis and convexity arguments, the authors show that the mini-batch method steadily reduces a natural measure of errors towards zero at the rate of O(1, k plus 1, m), where k is the number of iterations and m is the batch size. The paper builds upon previous work on GP frameworks for solving general nonlinear PDEs, which views a numerical approximation of the solution as the maximum a posteriori map estimator of a GP conditioned on solving the PDE at a finite set of sample points. The authors formulate the problem as an optimal recovery problem, where the goal is to find a minimizer of the objective function. 1.1 in a reproducing kernel Hilbert space, RKHS, U. The objective function, 1.1, consists of a regularization term and a data fitting term, where lambda is a small regularization parameter. N is the number of samples in the domain. Phi I, U, minus y encodes the PDE equation satisfied at the ith sample, and phi I represents the linear operators in the ith equation. The authors denote by phi the vector of linear operators, kappa the kernel associated with U, and omega the domain of the PDE. Gaussian process, GP, regression is a widely used approach for solving partial differential equations, PDEs, which can be formulated as a minimization problem. The representer theorem provides a solution to this problem, involving the inversion of the covariance matrix. However, this inversion leads to a cubic computational cost with respect to the number of samples. To address this issue, low-rank approximation methods have been proposed, but they lack scalability compared to neural network-based algorithms. GP methods offer solid theoretical foundations and provide uncertainty quantification, essential for establishing confidence intervals and deciding the placement of collocation points. However, the computational cost of n cubed hinders their scalability. In contrast, neural network methods excel in scalability due to the use of stochastic gradient descent (SGD) algorithms with mini-batches. This paper proposes a mini-batch method for GP regression inspired by stochastic proximal methods. Instead of pursuing low-rank approximations, the method stochastically solves the GP equation by selecting a small portion of samples to update the GP model in each iteration. This approach reduces the computational cost by only requiring the inversion of the covariance matrix of samples in a mini-batch. The proposed method reformulates the original problem as a stochastic optimization problem, which is then iteratively solved using the proximal map. By introducing a slack variable, the method encodes observations of the unknown function and allows for efficient computation of the GP model. The solutions of the reformulated problem converge to those of the original problem as the penalty parameter increases. This mini-batch method has the potential to scale GP regression to large datasets, making it more competitive with neural network-based approaches. The authors propose a mini-batch method for Gaussian process regression, tackling the infinite-dimensional minimization problem in equation 1.5. They derive a representer formula, equation 1.6, reducing computational cost to m cubed per iteration, using the standard Cholesky decomposition. Under assumptions of boundedness of phi and weakly convexity of the functions, phi, ni equals 1, the error diminishes at the rate of 1, k plus 1, m, where k is the number of iterations and m is the batch size. The method distinguishes itself from existing mini-batch approaches by considering the minimization over the latent vector z. It also contrasts with the stochastic Gauss-Newton algorithm for non-convex compositional optimization, which is not applicable due to the quadratic nature of equation 1.2. The authors note that their method does not eliminate statistical error, which arises from excluding a proximal step for U. Integrating this proximal step would require maintaining all minibatch samples and making the kth iterations minimizer UK dependent on the expressions of all previous minimizers U1, UK1, leading to higher memory demands. The paper first summarizes the GP method and proposes a minibatch method for solving PDEs in a general setting in section 2. Then extends the arguments and presents a convergence analysis of the minibatch algorithm based on stability analysis and error bounds in section 3. In Gaussian process, GP, regression, traditional methods face significant computational challenges, notably O, N3, computational time and O, N2, memory consumption for N training points. To address these issues, various techniques have been developed, including sparse GP methods, GPU acceleration, and stochastic gradient descent, SGD, methods. However, SGD methods are not suitable for this problem due to the need to minimize over the latent vector z in the objective function. The proposed minibatch method allocates computational burden to each iteration, ensuring robustness and efficiency. This approach is novel and has the potential to solve nonlinear partial differential equations, PDEs, in GP regressions with nonlinear measurements. The paper presents a minibatch method for Gaussian process regression, an approximation technique used in solving partial differential equations, PDEs. It begins by defining the data vector y and the nonlinear map f, then formulating the optimization problem to approximate the solution of the PDE. The authors also discuss how the minimizer of this optimization problem converges to the unique strong solution of the PDE as the regularization parameter lambda tends to 0 and the filled distance of samples decreases. In the second part of the paper, the authors propose a minibatch method to solve the GP problem with nonlinear observations. This method reformulates the original optimization problem into a regularized optimal recovery problem, introducing slack variables z and a new regularization parameter beta. The regularized optimal recovery problem aims to minimize the function phi, u, z, which consists of three terms: the regularization term on u, the penalty term for the slack variables, and the data fidelity term. The authors assume that the set X is a convex compact subset of R(P), where P is the sum of dimensions of the slack variables, and that X is the product space of a set of convex compact subsets, Xi(N), where Xi is a subset of R(Ni). This paper presents a minibatch method for Gaussian process regression, focusing on the minimization problem in equation 2.5 with constraints on Z. The authors introduce a minibatch version of phi, denoted as phi, u, z, I, which enables the approximation of the solution to the full minimization problem by sampling subsets of the data. This is achieved through algorithm 1, where the kth step updates, uk plus 1, zk plus 1, by solving the minimization problem in equation 2.10 with a randomly chosen subset IC of size m. The final approximation, uk asterisk operator, zk asterisk operator, is obtained by uniformly sampling k asterisk operator from 1, k. Notably, the authors highlight the practical challenges of solving the minimization problem in equation 2.11 for error analysis, suggesting that it is computationally expensive. As an alternative, they propose computing the value of u at a test point x using a minibatch I containing training samples near x. Another approach involves including test points in the training samples and solving equation 2.5 using the minibatch method. The paper also explores the possibility of extending algorithm 1 to incorporate a preconditioned variant, modifying the update step in equation 2.10 to include a positive definite matrix QK. This preconditioned approach maintains the theoretical foundations of algorithm 1, provided that the minimum eigenvalue of QK meets certain conditions. Finally, the paper discusses the reformulation of the infinite-dimensional minimization problem in equation 2.10 into a finite-dimensional one, utilizing the framework developed in 43. A lemma resembling lemma 3.3 in 29. is introduced to establish properties of a sampling operator, crucial for deriving a representer formula for equation 2.10. The development of a mini-batch method for Gaussian process regression aims to reduce computational costs associated with large datasets. Algorithm 1 iteratively updates parameters using mini-batches from the dataset. It begins by initializing parameters and then iterates through the dataset, solving an optimization problem to update the parameters at each step. The size of the matrices to be inverted depends only on the batch size, reducing the computational cost to O(m cubed) when using standard Cholesky decomposition. The authors also present two lemmas that support the solvability of the optimization problem and provide a representer formula for the solution. This formula, given in equation 2.15, expresses the optimal parameters in terms of kernel matrices and the observed data. It is derived by minimizing the objective function defined in equation 2.14, which includes a regularization term and a data fitting term. The paper discusses an alternative approach to dealing with PDE constraints in the optimization problem, involving the elimination of variables, which can further reduce the dimensions of the unknown variables, making the computation more efficient. This section presents a novel approach to Gaussian process regression that significantly reduces computational costs for large datasets. The authors introduce a mini-batch method for Gaussian process regression, enhancing the accuracy of algorithm 1 by replacing the term lambda mi, beta with a nugget eta r, where eta is a small real number and r is a block diagonal matrix. This refinement is crucial for achieving more precise results in the regression analysis. The convergence analysis consists of three parts: prerequisites, stability, and convergence analysis. In the prerequisites section, the authors recall basic notions of convex analysis, including normal cones, gamma-weakly convex and gamma-strongly convex functions, proximal maps, and Moreau envelopes. A crucial inequality, lemma 3.1, is established which will be used in the convergence analysis. In the stability section, the authors define the notion of stability for the optimization problem in a general setting. They consider a set of I.D. samples from a population and define the notion of stability based on the stochastic model xi u times x right pointing arrow r. This stability analysis is essential for understanding the robustness of the algorithm under different conditions. The convergence analysis section provides a detailed examination of the convergence properties of algorithm 1. By utilizing the established prerequisites and stability definitions, the authors demonstrate the convergence of the algorithm to the optimal solution. This convergence is guaranteed under certain conditions, such as the choice of step size and the number of iterations. The paper concludes by discussing the implications of the mini-batch method and its convergence analysis for Gaussian process regression. The authors highlight the potential applications of this approach in various fields, including machine learning and statistics. They also identify limitations and future directions for further research, such as improving the efficiency of the algorithm and extending it to other types of regression models. The authors introduce a mini-batch method for Gaussian process regression, focusing on the stability and convergence of the proposed approach. They define an operator G pro x underscore I psi, gamma which is used to approximate the minimization problem in equation 3.4. The stability of this operator is measured by its accuracy against perturbations of one sample, denoted by E. In lemma 3.2, the authors state that if G pro x underscore I psi, gamma is E stable, then the approximation of E xi, psi, U underscore I, Z underscore I, xi, using a mini-batch is bounded by E on expectation. The proof of this lemma involves showing that the expectation of the difference between psi, U underscore I, Z underscore I, and E xi, psi, U underscore I, Z underscore I, xi, is bounded by E, using the independence between I and I. The authors then move on to discuss the convergence of algorithm 1, assuming that all linear operators in equation 2.6 are bounded, as stated in assumption 1. They provide a remark on the boundedness of these operators, explaining that it is not restrictive if the kernel associated with the space U is smooth enough. This is illustrated through an example involving a linear operator phi and the reproducing property of the kernel. In Gaussian process regression, the mini-batch method relies on specific assumptions and properties of the functions involved. Assumption 2 guarantees the continuity and differentiability of functions phi, as well as their boundedness in terms of UF and HF. This, in turn, ensures the weak convexity of the objective function phi, and its variant phi, I. A crucial lemma, lemma 3.4, proves the micro-weak convexity of function high and its combination H, which is essential for the stability analysis. A subsequent corollary, corollary 3.5, demonstrates the lambda-Stromley convexity of phi, I, in U and its micro-weak convexity in Z. The stability analysis for algorithm 1 is established in lemma 3.6, which sets the foundation for the convergence study of the algorithm. This analysis is critical in understanding the behavior of the mini-batch method in Gaussian process regression. By examining the properties of the objective function and its variance, the stability of the algorithm is ensured, paving the way for a comprehensive convergence analysis. The mini-batch method for Gaussian process regression focuses on the stability of the proximal gradient algorithm, introducing a constant C dependent on several parameters for E stability. This approach omits the proximal step over U, reducing memory requirements. The descent property of the algorithm is highlighted, emphasizing the importance of step sizes and the expectation conditioned on randomness up to the kth step. Proposition 3.8 demonstrates the upper bound of the objective function's decrease, incorporating an error term dependent on the step size and the expectation of the next step's error. Corollary 3.9 proves the differentiability of the objective function, crucial for convergence. The proposed method efficiently manages memory while reducing statistical error, setting the stage for future research. The authors of the research paper present a mini-batch method for Gaussian process regression, focusing on the convergence of algorithm 1 in the setting of nonlinear measurements. They first demonstrate that psi in equation 3.13 is micro-weakly convex in Z, implying that nabla phi 1, gamma, Z, equals gamma, ZZ. The main theorem, theorem 3.10, establishes the convergence of algorithm 1 under assumptions 1 and 2. Specifically, it states that for a sequence, UK, ZK, generated by algorithm 1, there exists a constant C such that the expected squared norm of the gradient of phi 1, rho at zk asterisk operator is bounded by a term that decreases with the number of iterations k and the batch size m. The bound in equation 3.14 demonstrates that the error does not diminish to zero with an increasing number of iterations for a fixed batch size, but rather improves as the size of mini-batches increases. This result has significant implications for the practical application of Gaussian process regression, particularly in situations where computational efficiency is crucial. The authors then proceed to discuss the numerical experiments in the next section, which aim to demonstrate the efficacy of the mini-batch method. They solve a nonlinear elliptic equation and Burger's equation using Python with the JAX package for automatic differentiation. The implementation involves taking mini-batches with nearby samples, which are found using a KD tree to support the search for M1 nearest points in O, n log n, time and oxygen mononitride space. This approach allows for efficient computation and provides evidence of the method's effectiveness in real-world applications. In Gaussian process regression for nonlinear elliptic equations, a mini-batch method is proposed to improve computational efficiency. The true solution, U, is defined as sin pi x1, sin pi x2, plus 4 sin 4 pi x1, sin 4 pi x2, for x equals x1, x2, element of omega. The corresponding right-hand side of the first equation in the system, 4.1, is computed. A Gaussian kernel with length scale parameter sigma equals 0.2 is employed for regression. The algorithm utilizes 1200 samples in the domain, with 900 interior points, and a nugget value of eta equals 10^13. It terminates after 40,000 iterations, using the Gauss-Newton method to solve the resulting nonlinear minimization problem at each iteration. The results of a realization of the mini-batch GP method are presented with a batch size m equals 64. The sampling points and the contour of the true solution are illustrated in Figure 1a. The reduction in loss for the mini-batch GP method during a single run is shown in Figure 1b, derived from the average of the most recent 10 iterations. The explicit solution of U is given in Figure 1c. Figure 1d plots the approximation of U, denoted by UMGP. The pointwise errors of UMGP and U are presented in Figure 1e. For comparison, Figure 1f shows the contour of errors for the GP method using the whole identical sample sets, as described in 9. The mini-batch approach with a batch size of 64 achieves accuracy comparable to that of the GP method using the entire samples, demonstrating its effectiveness in reducing computational cost while maintaining precision. The mini-batch Gaussian process regression method is applied to solve Berger's equation, a nonlinear partial differential equation with an anisotropic kernel. In this experiment, 2,400 uniformly distributed points in the spacetime domain are used, with 2,000 points in the interior of the domain. The kernel chosen for this task is characterized by equation 4.2, with sigma equals 0.3, 0.05. The true solution is computed using the Kohl-Hopf transformation and numerical quadrature. The Gauss-Newton method is employed to solve the resulting nonlinear quadratic minimization problem, terminating when the error between two successive steps is less than 10 to the power of 5 or after a maximum of 100 iterations. A nugget value of eta equals 10 is used. Figure 2 illustrates the results of a mini-batch GP method realization with a batch size of m equals 75. The sample points and the true solution's contour are displayed in Figure 2a. The loss history generated by the mini-batch GP method in one realization is shown in Figure 2b, with a semilog scale on the y-axis. The explicit solution of U is plotted in Figure 2c, while the numerical approximation of U, denoted as UMGP, is presented in Figure 2d. The contour of pointwise errors between UMGP and U is shown in Figure 2e. The mini-batch GP method demonstrates a successful application of Gaussian process regression in solving a complex nonlinear partial differential equation, providing an efficient way to approximate the solution with a manageable computational cost. The choice of kernel and nugget value, along with the batch size, significantly influences the accuracy and efficiency of the method. The authors propose a mini-batch method for Gaussian process regression, demonstrating its application to solving nonlinear partial differential equations. In the context of Berger's equation, Figure 3 presents the averaged results over 10 realizations of the mini-batch GP method, utilizing varying batch sizes. The averaged loss histories in Figure 3a illustrate that increasing batch sizes yield faster convergence rates and smaller losses. The contours of averaged pointwise errors in Figures 3b-3d indicate that larger batch sizes achieve better accuracy, suggesting that a larger number of samples in a mini-batch is required for Berger's equation compared to the nonlinear elliptic example. This may be attributed to the lower regularity of Berger's equation, implying that uniformly distributed samples may not adequately capture the inherent regularity. This highlights the need for more effective strategies for sampling collocation points and selecting mini-batch points. The paper introduces a mini-batch framework for solving nonlinear PDEs with GPs, allocating computational cost to each iterative step. A rigorous convergence analysis of the mini-batch method is also provided. Future work includes extending the framework to more general GP regression problems, such as semi-supervised learning and hyperparameter learning, as well as investigating different sampling techniques to optimize mini-batch sample points. The authors discuss a mini-batch method for Gaussian process regression, acknowledging insightful discussions with Professor Andrew Stewart on the convergence of stochastic gradient descent. They proceed to prove two lemmas, starting with lemma 2.5, which involves defining a sampling operator Si and minimizing the function L, U, Z, I, with respect to U. This yields an expression for the minimizer U, used to prove the lemma. The authors then prove lemma 3.6, utilizing proximal operators and optimality conditions, establishing bounds on the norms of the minimizers and showing that the function phi is Lipschitz in a certain set B. This section is crucial for understanding the methodology and convergence properties of the proposed mini-batch method. The proof of proposition 3.7 continues with the derivation of an upper bound for the difference in the Gaussian process regression model's objective function values. Specifically, equations A.6 to A.10 establish a bound on the difference in the objective function values between the current and previous iterates, using Jensen's inequality, corollary 3.5, and lemma 3.1. This bound is crucial in demonstrating the E-stability of the proximal operator G pro xi, phi, gamma. The proof of proposition 3.8 is also presented, focusing on the convergence analysis of the mini-batch method for Gaussian process regression. By leveraging corollary 3.5, lemma 3.1, and the strong convexity of the objective function, equation A.11 is derived, relating the difference in the objective function values to the distance between the current and previous iterates. Lemmas 3.2 and 3.6 are then used to establish an upper bound on the expected difference in the objective function values, as shown in equation A.12. Subsequently, equation A.13 is used to analyze the convergence of the iterates, and by plugging in the iterates Ug, Zik, from equation 3.10, the expected difference in the objective function values is bounded in equation A.14. This bound is essential in demonstrating the convergence of the mini-batch method. The authors conclude the proof of inequality 3.12 by using the definition of phi1 rho in equation A.14. This results in an expression bounding the expected value of phi1 rho zk plus 1 in terms of phi1 rho zik rho gamma k micro and ek zk plus 1 minus zk 2. This inequality is crucial for establishing the convergence guarantees of the mini-batch method in Gaussian process regression. The page also includes a comprehensive list of. The paper concludes with a comprehensive review of Gaussian process regression methodologies, focusing on applications to large-scale datasets and complex systems. It emphasizes the importance of sparse approximation methods, such as inducing points and random feature expansions, for reducing computational costs. Mini-batch optimization techniques are also highlighted for handling big data in machine learning tasks. The significance of physics-informed neural networks, PINNs, for solving forward and inverse problems involving nonlinear partial differential equations is discussed. PINNs incorporate physical laws into the loss function, allowing efficient approximation of complex PDE solutions. The connection between Gaussian processes and deep learning is explored, including kernel interpolation for scalable structured Gaussian processes, KISSGP, and the orthogonal random features method for efficient kernel matrix approximation. Online convex programming and generalized infinitesimal gradient ascent are also discussed for optimizing hyperparameters.